The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
In our next presentation, we have two presenters. Patrick Power here is a grad student at University of Laval. In Shotcrete, University of Laval has a division that just specializes in educating Shotcrete people. Louis Sam actually got his master's degree there and is currently a civil engineer with CEP Forensic Consulting, a firm specializing in forensic engineering services. He's involved in several projects related to fire protection, building envelope, concrete deficiencies, and structural failures. So he has his master's degree from Laval in Shotcrete transport properties. He's an active member of our 506 committee and 216 on fire resistance, fire protections. He's also a chapter officer for the ACI Quebec in Eastern Ontario chapter. Gentlemen, and if you can keep it 30 minutes or around there.
Short and sweet.
Right?
Short and sweet.
Yeah. So we want to, I think that we rush through here and we really have a chance for questions.
Okay. Well, good afternoon, everyone. Thanks for staying for this last presentation. My name is Louis Samuel Bolduc. I'm going to present with my friend Patrick Power today. As announced by the title, we're going to talk about ServiceLife Prediction of Shotcrete, and we're going to pitch a couple of key elements of an ongoing project that's going on at Laval right now. A few words on the background. As you probably all know, in the last decades, a lot of changes happened in the construction industry, mostly powered by economical and environmental changes. So today, owners and engineers ask for more durable materials, so they want to reduce their maintenance costs and extend the service life of their structure. And this has brought up the concept of service life prediction. Now, in the concrete industry, those changes came along with performance-based specification and models that allow a quantitative evaluation of the durability of concrete. Now, a lot of work has been done on regular cast-in-place concrete, but very few information is available on that subject for Shotcrete specifically. Now, why would we want to study the service life of Shotcrete specifically? The answer to that question is that, and this contradicts what Lars said earlier, but a couple of properties of Shotcrete are a bit different compared to regular cast-in-place concrete. The first one is boiled water absorption values and volume of permeable voids are generally higher than that found in similar concrete. Also, the compaction and mixing energy is quite different compared to what we found in cast-in-place concrete. However, even with these higher absorption values, it is generally reported that Shotcrete can have an excellent durability. Another aspect that triggered this research project was that in the Shotcrete industry, the spec usually called for a maximum value of boiled water absorption from the standard ASTM C642. And for those of you who attended the 506 committee meetings, you know that this was hot topic because with the higher boiled water absorption, contractors and producers have to modify and improve the mixtures at great cost. And this has brought a lot of discussion. What we have here is what was the main reference in terms of boiled water absorption for Shotcrete. This is a table that was built by Mr. Rusty Morgan in the 80s. In his study, Mr. Morgan, from existing structures, he compiled several boiled water absorption results and linked the result with the quality of the structure he observed. Now, this is a very useful table because it's easy to use, it's cheap, and it's quick. However, it's important to understand that it can lead to misleading results because it was used by engineers as a durability criterion. And this is, we'll discuss about this later. Now, why this table can be misleading is that it is now well known that contaminant ingress in the concrete porosity to different transport mechanisms, such as permeability, moisture diffusivity, ionic diffusion, capillary absorption, which are all different physical phenomena. And this is very important to understand this because the boiled water absorption test only indicates the capillary absorption. Also, depending on the environmental exposure to which the structure is exposed, it doesn't necessarily mean that the boiled water absorption will be the relevant test. So we saw that there's no existing data on Shotcrete ServiceLife and that a questionable test is used as a durability criterion. So with this information, there was a need to go further on that subject. And that's what triggered the research project. A series of projects were undertaken at Laval University to address this problem. The objective of the project were first to generate data on Shotcrete transport properties and eventually to compare them to regular cast-in-place concrete and to offer guidelines for engineers to help them specify relevant material information. Apart from compressive strengths, what else should we specify? Boiled water absorption? Should we go into our rapid chloride penetration tests? Should we go further? That was one of the objectives of the project. Now, the project was divided in two phases. The phase one, which was my master's project, was it was between 2007 and 2009. We performed a complete characterization of several cast-in-place and sprayed concrete mixtures. And the objective was to explore the relationship between the boiled water absorption and the mix design, the shooting parameters, such as the speed of impact, the pre-dampening, and so on, and to evaluate if there's a relationship between boiled water absorption and rapid chloride penetration tests. Another objective of my project was to generate preliminary data on stadium, which we'll discuss later, for ServiceLife Prediction. Now, based on my results, Patrick's project is a phase two. His objectives are to perform a complete characterization of more focused mixture selection based on the results we have already, to confirm or invalidate the data from phase one, and to perform refined analyses using a ServiceLife prediction software. Now, we're not going to go over what was done in phase one in detail. We're just going to talk quickly about one key element. I'm not going to bore you with the details of the experimental program because it was already published and it was presented in St. Louis in 2008. But I just want to look back at one key results, which is the relationship between boiled water absorption and RCPT results. So to assess the correlation between these two tests or these two test results, data were plotted on a graph, what we see here, which is the RCPT results against the boiled water absorption results. It's important to know that RCPT is a test to estimate the ionic diffusion of the material. And I say estimate, it's not necessarily dead on. And capillary absorption is a test that evaluate the capillary. The Bolduc absorption test is a test that measures the capillary absorption. What we see here are the limits that were set by Mr. Morgan in this table that was discussed earlier. And these are the results from the Shotcrete mixtures that were characterized in our lab in Laval. So at first sight, we see that there is no direct correlation between the two tests. But to go a bit further, what you see here are limits that we found in ASTM C1202, the RCPT standard. And those are limits that indicate the chloride ion penetrability. Okay. So what we see, and I want to bring your attention on two things. If you look at the strip below the gray zone, you can have results ranging from, with the boiled water absorption results ranging from marginal to excellent. On the flip side, if you look at the left strip vertical, you can have all mixtures that would have been qualified as excellent for their boiled water absorption results, but their chloride ion penetrability ranges from very low to high. So this is very important, this graph here, because two situations can occur. The first one, if you look at the little point at the bottom right, this is a mixture that is qualified as very low penetrability, but the mixture would have been rejected because it's marginal, based on boiled water absorption. If you look at the results up there on the top, the mixture would have been classified as excellent based on its boiled water absorption, but the RCPT tells us that it has a high chloride ion penetrability. So this graph points out that there's no, the absorption test can lead to misleading information. We wanted to understand why these data were so scattered, and we realized that all the mixtures in the cloud down there contain silica fume. The mixture here contains fly ash, and the one up there contains only ordinary Portland cement. So we see the influence of supplementary cementitious materials. So this brings us to the part where we talk about ServiceLife Prediction. So what we just saw from the results from phase 1, it appears that there's the boiled water absorption poorly correlates with the rapid chloride penetration tests. And it is also to be noted that RCPT does not necessarily help owners and engineers to estimate the service life of their structures. It gives you Coulomb results of the RCP test, but it doesn't necessarily tell you how many years you can expect your structure to remain in acceptable condition. So the next step in our investigation was to answer the following question: how can we predict service life of Shotcrete? So there are numerous models that are available to predict the service life of concrete. And here, when I'm talking about service life, it's mainly related to the time to initiate corrosion. It doesn't include the freeze-thaw effects or others. So there are numerous models, and it is worth mentioning that these models are no longer only used in the lab for research. They are used in real projects. You will find clauses in contract document that goes, concrete shall have a service life of blah, blah, blah years. So this is becoming more and more common. It was the case, for instance, for the Panama Canal, but for smaller projects such as parking structures, rehabilitation projects, or any other structures for which durability might be a concern. Now, as I said before, very little information is available for Shotcrete specifically. So what we did in our case, we performed several tests that are required as inputs for service life prediction. And I'm talking here about a migration test, which is a modified version of ASTM C1202, the regular boiled water absorption test, an in-house drying test, and we made an analysis of the pore solution of the mixture tested. With these results, we were able to use these input in a ServiceLife Prediction software called Stadium. Now, Stadium is a numeric tool that predicts the ingress of corrosive species in cementitious materials. Inputs that are required for this software are the test results that I presented on the last slide, the material properties, that is water binder ratio, chemical composition of binder, and so on. And very important, the environmental exposure, because it's not necessarily going to be the same if it's a dry dock or a pier or the beam of a bridge. And with these inputs, the model is a multi-ionic model that considers both mass and energy transport equation and chemical equilibrium equations that are necessary to understand how the contaminant increase. It is, obviously there could be a lot to be said on this software, but it is not the intent today. We just used it as a tool to generate data on Shotcrete ServiceLife. So we're going to leave it like this for this presentation. So I'm going to give the mic to Patrick so we can explain what we're doing with this software.
Thanks, Sam. This is the first part of the Stadium part of our project. Essentially what we have here, there are two things I want to point out on this. The first is the geometry of the structure that's being considered. Essentially, we decide what type of geometry we want to use to simulate the conditions that you would have in situ. The second is the environmental exposure that you would consider for that structure or for that section of the structure. For example, the location we are considering is Quebec City. The exposure type is seawater. You can see, let me just see if I can put this up. You can see here that this structure is saturated on one of the surfaces for a short period of time. As a matter of fact, the chloride, there's a chloride content here. So it's it's completely submerged for part of the year. And then for the rest of the year, it's actually dried at humidity about 70%, which is normal for Quebec City. So that's how we design our simulation. You can also vary temperature. You could take this and change temperatures. You could also change the amount of chloride that you're considering. Is it seawater? Is it de-isorsol? That can change. You can also change, evidently, the humidity percentage. Another thing I was going to forget to mention is that we are considering 20 years. So this simulation is going to run for 20 years. For this simulation, we considered 4 mixtures. So simultaneously, 4 mixtures can be considered for that geometry. The first one is a control mixture from the SUMA data bank, part of the Stadium. Water cement ratio of 0.45, a binder content from OPC and silica fume, 8% silica fume replacement. The two other mixes we considered are both dry mix and wet mix with silica fume. The first of which has a water binder content of 0.51 with the 10% replacement of silica fume. Third mix, wet mix Shotcrete, a water binder content of 0.40 with 8% replacement. The last mix we considered in this specific example is a dry mix mortar, which has a water binder content of 0.47 and a 12% replacement silica fume with type 1 OPC cement. So this is what it looks like once it comes out. First of all, let's start with the axes. The first is X. This is the duration of the simulation, 20 years. You can change that, but we decided to start out with 20 years. The Y-axis is the total chloride content at 25 millimeters, about an inch. You could also change that. You could consider 2 inches, 3 inches, 1 inch is, for example, you could consider that as a bad cover for concrete. So let's be critical here. That's 25 millimeters. What you have essentially is the SUMA mix on top, followed by the dry mix, the wet mix concrete, and the mortar at the bottom. Essentially, you can see here that according to the simulation and the exposure, both considering the chloride content I just mentioned and the humidity, you can expect about 14 years service life, rather 14 years before you hit the critical threshold A critical threshold we chose for black steel, followed also by the other mixes which follow shortly after. Now, let's do something interesting. Let's compare that to the volume of permeable voids, which was measured using ASTM C642. What you have essentially is it doesn't correlate with the volume of permeable voids. If you were to base your design, or rather your choice of mixture design, on ASTM C642, or rather specifically the volume of permeable voids, you would have chosen either the wet mix concrete or the Summa concrete. Now, according to this, the Summa concrete would be the first one to go. Another thing is that there's quite a difference between 11% and 15%. For those who know, who've tested, who've used ASTM C642, 4% for that is quite a difference. The other thing I wanted to point out, actually is coming up right up. What happens if we consider ASTM C1202, RCPT, that we presented just earlier? Well, this time it's not so bad. I'll get to later talk that about, a little about that, but so it doesn't seem so bad. You have, for example, the dry mix concrete that hits at 1418 coulomb, just as a rough value. Remember, it's between 0 and 9,000. 9,000 is a critical value that you rarely get, and you want to go around 1,000 to 3,000 for something standard, where under 1,000 is excellent, according to the ASTM, according to the norm, that norm. So this is not so bad. It actually somewhat correlates with this analysis. However, that's only for 3 mixes. What happens with the rest of the mix design that exists in industry right now in North America, and as a matter of fact, the rest of the world? This is only for 3 mixes, and so that's what really motivated us to keep going with that. So based on results from phase 1, we decided to go further with that. We decided to expand the mix designs that could be represented for industry. And with the goal we had in mind was the goal that Louis-Sam just mentioned earlier. We wanted to have essentially information and hopefully a line drawn to service life assessment of Shotcrete. These are the mix designs we selected. Actually, these are the mix designs we got offered by industry because we wanted mixes from industry. I'm just going to go quickly here. There's a lot of details. This is essentially what it is. The first 3 are mortars. The first 2 are dry mix mortars. The third one is a wet mix, all OPC with essentially the same ACI number 1 grading. The second group of mixes is silica fume shotcrete, so coarse aggregate, both dry and wet mix. These are common in East Coast Canada and United States, Northeast. The third mix to be considered is a ternary binder, where the ternary binding agents are actually just OPC, silica fume, and fly ash. This is sometimes, usually more found in the West Coast and Vancouver. This is actually where the mix is from, Alberta, Vancouver. The control mixes, because you got to have control mixes. We have a dry mix and a wet mix, again with the same course, the same grading, aggregate grading, just to have an idea. So welcome to the Shotcrete lab. I just wanted to put this picture here so you'd have an idea what it is. Sorry about the mess. We just finished shooting. You can see the dry mix machine here we're dismantling to clean up. The room right there is where we shoot to contain some of the aggregate. And you can't see it, but the rebound panel is there. It's connected to a computer, which you can't also see. But essentially that's where it is. That's where the magic happens. Now, how do we shoot the material for phase 2? We wanted to control the shooting energy into our panels. This is something that one of my colleagues, Nicolas Genous, is studying as part of his doctoral studies. So we wanted to control the shooting parameters. How do we do that? Well, first of all, let's represent industry. Let's shoot perpendicular. You want to have maximum impact energy, so let's start with that. Followed by 2 other things. The first is the distance. We're going to control the distance at about 1 meter, give or take an inch or so, so 3 feet, 4 inches. And we also want to control the airflow. Now this is 200 CFM. We chose 200 CFM as it's slightly over what we consider in-lab optimal conditions, just to get a little compaction, just to get a little more compaction than you would need. This is the airflow that's measured in the nozzle, not the airflow you would see on the compressor, for example. What does this allow? It allows identical shooting energy. Essentially, it locks in a lot of variables that would otherwise provide a lot of variability in itself, in terms of energy, how it compacts. So what happens? We shoot 5 panels. For all the mixes considered, we shoot 5 panels. 3 of the panels are cored. 2 of the panels are actually sampled directly from these panels, avoiding essentially about an inch from the bottom. We don't want to have too much paste in it. We want a representative sample. And so the 2 panels that we sample, we put into an 80-liter planetary mixer. This provides a lot of samples to test with. Essentially, for the cord, we want to have 3 times the 3 panels, so 3 sets of samples to test. And that's actually very interesting for dry mix because there is some variability in dry mix. We want to evaluate that. And finally, so for the batch, we produce normal compression cylinders, 4 inches compression, 4-inch compression cylinders. We also produce panels that go from about this big to that big, from about 2 feet to about 1 foot. We want to do a quick imagery analysis, something that's been in the works at Laval. Instead of doing an L-bar, we just want to have an idea of how the voids, the large voids are spaced in the samples. So that's another thing we're considering. Now the testing program is pretty much the same as my colleague in phase 1. We have the standardized tests, the compression strength tests in the top, followed by the C642 and 1202, and of course the tests that are required for stadium analysis that we input into Stadium Lab. So, and followed by the imagery analysis, which I won't get up very much into, but it's a very promising prospect. Now, here are some preliminary results. There's a lot of numbers there. I just wanted to point out one thing with this. By the way, x-axis is the water binder ratio, and the y-axis actually both the compression strength. Both on the left side is MPa, on the right side is PSI. This is at 28 days of curing in a moist room, 100% moist room. What I just wanted to point out with this was that all the mixes are over the 4,000 PSI limit, which is often discussed in committee. That's the only thing I want to point out. The other interesting thing I wanted to say, but essentially that the water binder ratio is across the board, and it doesn't necessarily correlate with compression strength, and that's because mix design has a lot to do with it. Not just water binder ratio, but what type of aggregates you have, what type of binders you use, what type of how much binder you have per cubic meter, for example. It plays a lot, and so you can imagine how that plays into durability. So this is another one. Here's boiled water absorption as a function of in-place paste content. So this is how much massic paste you have in your mix once after it's been shot. You can see in blue is the wet mix, in black is the dry mix. Here are just a few examples. There seems to be, actually this is a trend that my colleague in his work came out or took out, and essentially what it is that boiled water absorption is somewhat, correlates with paste content. And that's one thing that's quite interesting. The other thing is that there seems to be an effect with aggregate, but we won't get too much into that. So that's one thing. The other thing, yeah, so there you go. These are generally the trends I just wanted to point out. And then what about graphite chloride penetration? This is something else. The one thing that is worth mentioning here is that all the mixes in the bottom are silica fume. There's a lot of literature that exists on the effect of silica fume and as well as other cementitious materials in ion transport, or rather in conductivity of the pore solution. So if you look in literature, you'll find out that silica fume plays a big role in that, and that these results may not necessarily represent equivalent OPC material. Other than that, these are just a few select samples, and I just want to give you guys an idea. This is at 56 days to take into account the pozzolanic effect of silica fume and other cementitious materials, supplementary cementitious materials. So in summary, let's just recap here. We've presented results from standardized tests, and they're useful for quality control. This is actually something that Mr. Bolduc just presented just a second ago. If you know your mix ahead of time, there's nothing wrong with testing it again with these easy and these tests that are really relatively cheap and quick to make. It's great for quality control. The thing is, do we know how long it's going to last based on a cool-out rating or based on boiled water absorption or volume permeable void? Can someone stand up and say, well, that one has 12.4% of volume permeable voids? and say that's going to last 67 years. Probably not. And that's what we want to get to. So we are adapting tests to get a broader understanding of the microstructure of the samples, and therefore we use the tests that are provided by the Stadium Lab format. So the results aim essentially at providing three things. The first, and Louis-Sam this is pretty much the underlying theme of this whole project, is that we want to compare cast-in-place concrete with shotcrete performance. We also want to better understand transport properties of shotcrete, as it has not been researched in the past. The third thing is that we want, and this is what we want to provide at the end of this project, we want to provide groundwork for development of new shotcrete performance specification, something which today in modern times is becoming the standard. So essentially what's next? Well, this is a few. I just wanted to put a few pictures of what the project looks like in the dirt. In the bottom left, you can see this is what the drying test looks like. You have large 50mm samples and smaller 10mm samples. They're left in a 50% room to essentially dry up slowly, and you measure the loss of mass. Center bottom, you have migration tests. These large cells, about 2.5 liters on either side. Principle is similar to RCPT. And in the top, you have the imagery, and that's what it looks like. On the left, it's just a panel that's been pasted over. We're going to sand to get those big voids out, just to get a broad idea of what does it look like after we shot it as a hard material. So after that, once all the batching and all the wet work is done, we'll take all these shot mixes and batch mixes, and then we'll process them with the results through Stadium Lab, and then Stadium analysis. We'll vary, as we presented with the dry dock, we'll vary environmental conditions for representative. So in these mixes work, would they be used in coastal areas? Would they be used inland for road infrastructure? And what type of salt environment are we considering? Are we considering a saline environment? Are we considering a de-icer salt? So, and that changes because the tide is essentially daily, but de-icer salt only happens, the flow of de-icer salt happens in the spring. So that's something interesting to consider. And also geometry is going to be something interesting to consider. And finally, once we have all that data, we can compare it to the SUMA data bank for just further analysis and comparison. So thank you very much. We just want to take a second to thank the American Concrete Institute for the time they allowed us to present this, as well as the ASA for the ASA, Laval, and Simcoe and CAP for their support, their kind support throughout this project. If you have any questions, we'll be right here. Yeah, right on time to sashay over to the mixer. So thank you very much.